Thank you. First of all, I'd like to apologize. I'm not the Dr. Amal Pouna that was promised to you. He couldn't be here, so I'm replacing him. Second apology, I'm also not a hydrogeologist. So all the difficult questions, I gladly refer to ap@traqa.be, and please bug my colleague Amal, who couldn't be here today. Okay, let's get started about EPU-Karst. So EPU-Karst is a project that is kindly paid by SPGE. It's a Belgium, or rather Walloon organization in charge of water monitoring. And it's coordinated by QEPS, who is an NGO responsible for research of karst systems in Wallonia. So EPU-Karst is a research project in 2 phases. It started in 2019 and is still ongoing. So the first phase does not yet involve the drinking water producers that you see in the title. It's more like an experimental approach, and it involves a lot of, how do you say it, volunteers. So it's more like a citizen science project, the first phase. And then the second phase that started only last year, there is the phase that involves the drinking water production companies. So just to give you a general context, so we are located in Wallonia, which is in the south of Belgium. As some of you might know, there's a big difference between the north and the south. We don't agree very well politically. We don't speak the same language. And even on geology, it's very different. The north is very much flat, a lot of sand silts, very similar to the Netherlands, while the south actually has a lot of karst systems. And in terms of groundwater, drinking water production, it's very important as well, because 80% of drinking water production in Wallonia comes from groundwater. Of this 80%, 50% more or less, even more, as you can see here on the pie chart, comes from primary kalk, also limestone systems. Unfortunately, like many karst systems, there is a threat to the groundwater quality. Here we are focusing on nitrates, that is mostly coming from agriculture and just population density. So the point of the goal of the EPU-Karst project was to see, first of all, how this nitrate enters and behaves into the karst systems, and if the karst system has a role in storage and transfer of nitrates. We also wanted to see if there are trends between different karst systems in catchment sites in Wallonia, and if we can see also differences between different compartments, or I can say karst features, maybe in English, between shallow holes, the unsaturated zones, underground rivers, etc. So a little bit more in detail. This is, again, a map of Wallonia. In light blue, so yeah, this light blue is all the limestone aquifers. And the dots that you can see, the yellow dots, green dots, orange squares, indicate the nitrate content. So the greens are still okay. It's between 10 and 25 microgram per liter, but we have also zones that are a little bit less okay. So the yellow dots, the orange ones, 40 to 50, and even a zone where we go above 50 microgram per liter. We have to know that in Europe, they set the limit for drinking water at 50 microgram nitrate per liter. So these zones are no longer accessible for drinking water production, which is, of course, very problematic. So now about the first phase. So this is the experimental approach. This does not yet include the drinking water producers. But here we worked with volunteers, mostly speleologists. So we have, for the first phase, 5 different sites were selected. And these sites were selected on very specific criteria. So all features had to be available and accessible in the karst system. So we wanted to have access to swallow holes, to the non-saturated zones via drip systems. We wanted to have an accessible ground river, and also the final spring. So these were criteria, like the first set of criteria that's needed to be available there. On top of that, we also wanted to have 5 systems that were very different from each other. So we wanted to have some karst systems with a lot of sinkholes, another one with very few sinkholes or swallow holes. We wanted to have a lot of drip systems, few dip systems. So a lot of variety within these 5 systems. And also the location had to be very different. So some were close to urban areas, others were Furfoots, for example, which is number 2, is actually a natural area. So there's only forest on top. There's no urban activity. There's also no agriculture nearby. But there are other systems with more agriculture activity. So we chose these 5 sites, and each site had a speleology club assigned to it, with one manager that was managing this site. We were very lucky to find a lot of volunteers that were helping us with this first phase of the research. And during 3 years, so the 2019, 2023, but the actual sampling only began in 2020. During 2 years, they sampled these sites every 2 months. So we did a education program of this group of volunteers, the group of speleologists, to use different type of tools, field tools, for example, for temperature probes, pH, dissolved oxygen, and of course nitrate probes as well, which was a portable spectral photometer. These samples were also, all this field analysis were also compared with samples in laboratory tests, just to be sure that they sampled correctly. So if we look more as an overview of the methodology during this first phase. So they sampled in these 5 different locations. Also something to note that the hydrogeology of these 5 locations was already known previously. So it was not part of this EPU-Karst project, but these caves were already studied by universities, usually beforehand. So the speleologists were trained to use the monitoring instruments, but also to sample, to analyze the data, and to report the data. All the data were reported on the EPU-Karst website. So again, they sampled every 2 months, and this for a period of 3 years. On top of this citizen science with these volunteers, there was also a lot of education done by Webs, which is the coordinator of this project. So there were field trips with the general public, there were flyers, booklets, there was a conference, a lot of things were done to really inform the citizens about this nitrate problem. So as a result, over 10,000 data were collected by these cavers, which is quite impressive because they did it quite consistently over 3 years. This means that there were in total about 110 sampling days, and they sampled in these different karst features that were available. So in drip systems, which you could see on the first slide, they sampled in these little basins, basically. In the saturated zone, so underground rivers, and of course at the source as well. Now for the results. So this looks a lot, but I will guide you through it. So on the x-axis, so these are of course the 5 different sampling sites. On the x-axis, you can see all the different sampling sites within one karst system. On the Y, of course, the concentration of nitrates. And then each feature has a different color. So you have the gray, the swallow holes, in yellow, the unsaturated zones, so the drips. Then the final karst spring, the surface water was also sampled. And in dark blue, you have the underground river. Now, what is quite peculiar here, first of all, we see that the swallow holes usually or always have a lower concentration in nitrates than the unsaturated zone, so the drips, which seems a bit counterintuitive, because in general, we think that the swallow holes are kind of a highway of pollutants, and this is not what we see here. So the concentration in the swallow holes is lower for each system. So this is a general trend, except for furfos. The furfos is kind of a strange system because it doesn't really have the karst is not fed by a sinkhole. Actually, what furfos is this natural reserve, this natural area. Furfos is actually just a lesser river that goes on the ground and then just leaves the furfos system again. So this is just a surface river that temporarily goes on the ground. This is not fed by swallow holes like the other systems. So this is one quite peculiar thing that we can notice in all systems. Another peculiar thing is, well, maybe it's not that peculiar, but the value of the underground karst river is kind of the same as the final karst spring. So there's no change from the underground river to the spring. The nitrate concentration remains similar. And this value is, which is maybe less surprising, this value is more or less between the values of the swallow holes and the higher concentrations of the unsaturated zone. Then another peculiar thing is, if you look at the values of the karst springs, in each system, this is higher than the values of the surface downstream water, which is also maybe counterproductive, because usually we say, or we think that surface waters are more contaminated, there's more runoff, so they are usually have, or at least we think that they have a higher nitrate concentration. But we can see here that it's actually the karst systems that feed nitrate to the surface water. So these are unusual or conclusions that we didn't, or results that we didn't expect. So this is first surprise of the first phase of this study. This is just to summarize what I just said. So we have higher concentration of nitrates in the karst springs compared to the surface water. The swallow holes have a lower concentration compared to the drips. And this is similar in all systems, despite that they are very different from one another. This is a trend that we see in all the systems that were studied in this first phase. So again, same conclusion, but now we see it on a picture. Now, after this first phase was finished, we started with the second phase, of course, taking into account the results of this previous work that was done during the experimental phase. This only started last year, so we don't have that many results yet. But the second phase did include the drinking water producers. So now, of course, we chose other sites, 5 other sites to study, because the first sites were not drinking water producers. And we applied the results and also the way of monitoring and the monitoring tools that were studied during the first phase. There's also drinking water producers in Belgium. I think it's a European requirement, but in Belgium, they are required to sample manually 4 to 12 times a year. This depends on the size of the drinking water producers. So smaller producers only need to sample 4 times. Bigger producers need to sample every month. And of course, this is not very much. So we, in the second phase, as part of the project, we aimed to measure continuously the nitrate concentrations. With the objective, of course, there were 2 big groups of objectives. So the short term was to really identify the variability, the trends in variability of nitrates, because this was not possible with 4 to 12 manual samples a year. And also in general to improve the hydrogeological knowledge of their karst systems, because we noticed that a lot of water producers don't really know how their catchment works. They know the spring, they know the quality of the spring, but what happens all before that, they don't really care as long as it doesn't really affect the quality of the water at the spring. So this was short-term objective. Then, of course, in the long term, with these results, we want to provide these drinking water producers really with the tools and the knowledge to better manage their drinking water sites, because of course nitrates, but also other emerging pollutants are becoming a bigger and bigger problem, and they need to really manage this system. So this looks really scary. On top of that, it's in French, but I just want to show you a few important aspects. So first of all, what we want to achieve with EPU-Karst is to know better this storage and transfer in non-saturated zones, which was actually more important even to the contribution of nitrate than the swallow holes. What we already know, or what we already have information of, is the flux entering the system, and of course the ones getting released at the catchment sites of the drinking water producers, because this is what they monitor. We know how many nitrate enters the system because there's this organization called Protect O, which is linked to EPU, which was the financial contributor of this research. They actually take soil samples regularly, and they measure the nitrate content of the soil samples. They do this in collaboration with the local partners. In this case, these are usually the farmers, and also with just the local commune. And they do this because they want to make sure that no more fertilizer than needed is used during farming. So they kind of they analyze the soil on regular time periods, and they say, okay, now you have to use less fertilizer because there is too much nitrates entering the system. It's called APL in French, but in English, it's the potentially leakable nitrogen, I think. So that's what they measure. Of course, they also measure just the meteorological data, which is also done by the drinking water producers. Now, for the second phase, there were 6 water producers involved for 5 catchment sites, because there's 2 communes de Nassau and Ville de Rochefort actually use the same catchment sites. They are 2 very small communes. So 6 water producers, 5 catchment sites. If you go up to the next slide, we see the locations of these, and we also kept Vilaine-Source, which is the same site which was used in phase 1, just as a comparing site. So yeah, about 5 sites for 6 water producers. This was some of the results that they gave us. So this was from their manual sampling. You see Payenne is a slightly bigger site. They sampled a little bit more, and the concentration remains quite stable. Well, it increased a bit, but still reasonable. Neuffontaine, on the other hand, has a little bit of an issue because the nitrate content keeps increasing, and it keeps increasing to the point where it's reaching this critical amount of 50, after which, if they reach 50, it's done and over. Like, they have to stop producing water or start mixing with other catchment sites. Anyway, this is very problematic, and they work together with this Protect O organization for already quite a while, which clearly doesn't really have an effect because it just keeps on rising. They sampled quite regularly between 2008 and 2014, but I don't know why they decreased the sampling. And you also see, of course, that you lose a lot of the variability data, which is kind of logical you sample less and suddenly you don't see all these details anymore. So that's what we wanted to contribute to the project. Each spring was sampled, like there was a nitrate probe installed at each spring. On top of that, temperature, electric conductivity, turbidity was also measured. Of course, we had the meteorological data. We also measured the hydrogeological budgets for each site. Of course, the routine sampling by the water producers continued because it's a mandatory sampling. And on some locations, we also did some additional sampling if we thought that was needed with a spectrometer. So for some of the results, this is the Neufontaine catchment site, which is getting in a critical condition. The black is just the water level measured within the cave. The blue, we see rainfall measures. The pink is excess water, I think it's called in English, if that's correct. And the green is the concentration in nitrogen. But if you see the green squares on top, these are the manual samples. So we see there's quite a big difference, especially at the beginning of the measuring period. So we really had to calibrate our instruments correctly and adapt some of the installation of the instruments to ensure that the automatic sampling actually is getting closer to the manual sample, which is finally getting better here at the end of the first year. So this is something that we had to learn at the beginning to calibrate the instruments correctly and install them correctly. This is another site, the Payenne site, who is luckily a little bit more stable. Again, we still need some work on the calibration. This is the water level again, the rainfall and excess water. Here, the nitrogen content is a lot more stable. This is also a site who doesn't have sinkholes or anything. So in general, the nitrate content is quite constant. This is for all the sites altogether. Again, this is not a good sign, but Vilaine Source, this is the one that isn't a catchment site. So the dark purple is the site that was already sampled in the first phase. This one has a lot of sinkholes. You also see a lot of variation in the results there. But of course, this is ongoing research, so we don't really know yet how we have to interpret the data and what the contribution factors are exactly to these different figures that we see here. So what we will be doing now in the second phase to really figure out what is the contribution of the unsaturated zone to the nitrogen in these different catchment sites is to really go deep in the hydrogeological investigations, because this is not really known yet for a lot of drinking water producers. They have the catchment sites, but they don't exactly know how it functions. So we will do a lot of tracer testing, which was already mentioned many times before, to assess travel times and the hydrogeological connectivity. We are very lucky because we have our instruments. We developed that ourselves at Trakwa, and we have 50 of them available. So Mr. Gunn mentioned earlier that it might be difficult to have 17. We have 50, which means that we can go really, really deep into the detail when we do tracer testing. So we can obtain a lot of data during one tracer test and hopefully get a really detailed functioning of the hydrogeology. We will also do geophysical investigations, or at least not us as a company, but as a consortium, to evaluate this depth of the soil cover, and also continue the measures of the potential leachable nitrogen, which is not done on all catchment sites. So this Protecto only works together with drinking water producers that are really reaching this critical level of 50 milligram per liter. So these are, of course, we just started last year, so there's still a lot of results and analysis that need to be done. But of course, we saw that high resolution monitoring is really necessary for nitrate. Otherwise, you will lose a lot of the data. You can also, I don't know if they actually did it, but you could also pick your moments if you only have to sample 4 times a year. We also saw that it's very important to calibrate your instruments correctly. There's also some learning phase required. We also saw some correlation with rainfall, but we don't know exactly yet how it works. So we hope that the hydrogeological studies will help with that. And for the moment, this type of very detailed work hasn't been done yet in Brussels, so it's in Belgium. So it's a first, and we hope that this project will really contribute to provide a lot of more information, a lot of knowledge about the catchment sites for drinking water producers in Belgium. And of course, the second phase of the project will also be very important to really understand how the nitrate is stored and transferred in this unsaturated zone. So there's a website that they continue to put data on, which is EPU-Karst.org. So if you're interested, unfortunately it's in French, but Google Translate is there nowadays, so they can help you out. And again, if you have difficult technical questions, you can contact my colleague AP at contact or just at contact@raqua.be.
Thank you so much, Sophie.